Hey all, welcome to Continuous Learning Week 2. This is the first video that we're going to be tackling this week as we continue to build on the notions of area that we introduced last week. To give a little bit of a recap, last week was a lot of building blocks, so let's kind of recap where those tools came into play and maybe where they'll be leading us next. So as we scroll up, you'll see here that the very first lesson we talked about last week was the idea of factoring. The reason this was very important for us to introduce is precisely because factoring requires us to take what are called quadratic polynomials, power of 2 in terms of our variable, and break them apart into smaller pieces. Now, this is especially useful when we talk about area because area is a two-dimensional measurement, meaning that if we are to measure a length and a width of something in terms of a variable, in many cases, we'll be able to deconstruct an area expression into this length and this width abstractly using factoring. So again, this was kind of a tool for us in that regard. After that, we introduced another tool, which is the idea of circumference and arc length, which was a way for us to talk about the distance we've traveled around a circle, as well as sections of that distance that we might travel, which is also especially interesting. And so really this was all proportional reasoning, and we looked at some more advanced problems where we were maybe using circumference and or arc length alongside other notions of perimeter that we have established in the past. Last but not least, we have areas of circles and sectors, which again, we talked about how the area formula for a circle is very foundational to where we're going to be building, especially as we start to see the connections with regular polygons. But also, we introduced this idea of sectors, which again, sectors being portions of a circle. They're like slices of pizza in a pie. So again, keep that in mind as we talk forward. These were kind of our foundational building blocks, working with two-dimensional expressions in the form of factoring, and identifying part versus whole relationships in terms of circles. Now, the last thing that we're going to talk about is an idea that really could be introduced later, but it is relevant when we talk about circles in particular. And today's section is going to be about what are called area segments, as well as annuluses. So to give you an idea of this, really what the idea of a segment or an annulus is it's really just what's left over after removing. Oh no, I can't write off my page. I thought I could. Oh well. So it's what's left over after removing a chunk. Okay? That's really what we're going to be talking about today. So you can think of donut shapes are an example of this, and you can actually see an example of this down here. This here is called an annulus, which the area of an annulus is really the area of a donut. And then we're also going to look at what are called segments of circles. Segments are, in particular, what happens when we literally take a segment and we cut off a section of the circle, which is kind of interesting as well. Now, you'll see in the practice that you'll get today, as you work with area segments and annuluses, you'll also work with some situations where you'll be looking at the area of a figure with other figures removed. So it could be a circle with a triangle removed and a diamond added back in. And again, you're going to need to calculate the area of these different portions in order to figure out what is the overall area. So again, to kind of build from this today, again, you can see this definition of talking about a segment of a circle. So a segment is really the area enclosed by the edge of the circle and a segment that passes through. This circle. Okay. Now, notice, again, this problem seems like it would be especially complicated. But the reality is with all of these problems, we're going to be relating these areas to other areas. So instead of finding this directly, this area of this segment, what we're going to do is we're going to find the area of this particular sector, right? Which again is a relationship between that and the area of the whole circle. So really, we're going to find the area of our whole circle, and then we're going to look in particular at the slice that we're interested in. And then we're going to remove the triangular piece that's created by the segment that is cutting across the circle and the two radii that we've drawn in here to define the sector. That will leave us with just the crust, or the sector. Now, how do we do that in practice? Well, first and foremost, this is one that's fairly nice to approach because you'll notice this triangle here is a 90 degree central angle. And in fact, something else we know is that this triangle is isosceles because both this and this are a radius, implying they're both 6 units in measurement. And so what that means is calculating the area of this particular triangle will be fairly straightforward. But before we do that, we might first want to find the area of the total circle. And as we know, the area is pi times the radius squared. So pi times 6 squared, which is 36 pi. Now, what we'll notice is that the section that we are looking at of this circle is a 90-degree section. So this is our sector. We're looking at a 90-degree section out of 360 degrees. And we want to know how big that particular sector is when we know that the total area is 36 pi. When we solve that, we will actually uncover that the area of the sector is 9 pi. So now we've really isolated and focused down on this particular sector right here. But now what we would like to do is we would like to officially determine the area of the segment by first finding the area of this triangle. Let's see if I can get a better triangle going. Great, the area of this triangle. And then we want to subtract off that area of that triangle from the area of the segment we just found. Well, the area of the triangle that we're looking at is going to be found by 1/2 base times height. Well, our base and our height are both 6 in this case, perpendicular measurements to one another, which means the area of that particular triangle is 18 units. So what's the area of that segment then? Well, the area of the segment, as we mentioned, is going to be the area of the orange sector minus the area of the dark blue triangle. So the area of the segment is going to be 9 pi minus 18. And this is actually an exact way to leave our answer. We could round this particular answer, but we could also leave it exact, which 9 pi minus 18 is precisely exact and is what we want. Awesome. Now, this is using a lot of pizza analogies, but again, you'll notice this is almost like you're cutting off a section of the crust. And the idea, as we build to the idea of an annulus of a circle, is thinking about the crust all the way around. So an annulus of a circle, which we're going to kind of build to next, is really just the area contained between two concentric circles. Now, if you've not heard the term concentric before, concentric means having the same center. So it means two circles that are of different sizes but are centered in the same spot, such that we get a perfect donut shape. And just like the segment problem, the way that we calculate this area is we find the area of the outer boundary, which in this case is the outer circle, and then we find the area of the inner boundary, which in this case is this smaller hole in our circle, and we take the area of the outer boundary minus the area of the inner boundary to leave us with the pieces in between. So as we go to explore that, we might say, well, then what is the area of the outer boundary? The outer circle. Well, in this particular instance, what we'll notice is that the radius of this particular circle, from the center all the way to the outer edge, it looks to be 10 units because it's 8 units in this central radius to the edge of the donut, and the donut appears to be 2 units thick. So that means our radius to the outer edge is 10 units, which means our area is pi times 10 squared, or 100 pi. Great. Well, what about the area of the inner circle? Because we need to know how much has been removed through this process in order to determine how much is left. Well, again, our inner circle has a radius of 8 units, which is 64 pi. So if someone were to ask us, well, what is the area of the annulus of the donut that's left if I remove the inner circle from the outer circle? And to find that, we simply subtract the outer boundary minus the inner boundary. What we're left with is 36 pi. That's the area of our annulus. And you'll notice that as we talk about problems like this, we can use ideas and formulas to help us evaluate more complex or involved word problem situations. But also we can use these ideas to look at the area of any object in which it has a hole of any shape, whether it be a circle, a rectangle, a square. And we can apply this principle of taking the outer boundary minus the inner boundaries in order to find the area that remains. Now, if someone were to give you a word problem like this and they were to not really give you much context, again, what you want to think about is the larger principle of things. I don't want you to really memorize a formula. What I want you to do is think about what an annulus actually is. It's what's left over after you've removed a hole, right? And with an annulus, it's always a donut shape is technically what an annulus will always appear to be. So in this particular instance, we're told the area of the annulus. This is what's left over. There was 176 pi. Where did that come from? Well, we know that the larger circle has a radius of 15 inches, and we know that our outer boundary, our larger boundary, is going to be the total area that we had originally, minus some inner boundary. But we don't know the radius of the inner boundary. We don't know how much we actually removed. In fact, we don't know what the radius was to define how much we removed. We just know how large the outer boundary is in terms of its radius, and we know how much area was left over. Once we have that in place, what we can do is simply simplify our process. For example, we notice that we have 225 pi minus a certain amount of pi r squared gives us 176 pi. Well, going about solving this, as we we'll isolate our term with our variable, giving us negative pi r squared is equal to, in this case, we have 25 and 24, so negative 49 pi. Those of you who are astute in this will notice that the negative pi's can be divided out as factors on either side, leaving us with the radius squared as 49, or the radius of the smaller circle must be 7. So again, to give us a depiction of this situation, that was a terrible attempt to draw a circle. We have a larger circle with a radius of 15 inches, and we have a smaller circle that is also centered in the exact same spot, which I did a horrible job of demonstrating. But we have a smaller circle with a radius of 7. So radius of 7 here, radius of 15 here. And that gives us an annulus with a shaded region. Ooh, small shading, but a shaded region of precisely 176 pi. And that right there, folks, is what you need to know about annuli of circles, as well as segments of circles. And in general, the larger principle here, the idea that we can look at the area of a figure and remove inner boundaries from that figure of various shapes, calculating that area and subtracting it from the total to find what's left of the Swiss cheese that we have after we've removed all these holes. Thanks so much for tuning in for video 1. Videos 2 and 3 are ready for you as well. Thanks so much. Have a good one.